I'm late. Okay.
I can hear you now.
Can you hear me?
Yes.
Good. Okay.
And I'll take control of the screen sharing again if you prefer.
So are other people hearing the white noise? It might be, it's possible. It's just the problem is at Juven's.
Yeah, could be.
And if other, well, I mean, that's how we do the experiment. So are other people hearing white noise? Because we've been trying to.
That's not.
No? Okay. Okay, well, Juven, you just let me know when you're ready to go.
We'll wait for like maybe 1 or 2 minutes, 2 more minutes. Okay.
Yep, I think so. Thank you.
Make sure original sound is off.
Ah, that's a good point. Yeah, it's now off. Yeah.
Noise actually no background noise.
It was original sound.
Yeah. Then
I had original sound on. That was it.
No, it's perfect. No, it's just perfect.
Yeah. Yeah.
So maybe we can gradually start and then me
Okay.
also coding. Just a second. Oh, by the way, we should have a Greg share the screen.
Yes.
Welcome everyone to Harvard CMSA Quantum Matter in Math and Physics seminar series. It is our great honor, really great pleasure to invite Professor Gregory Mo from Rutgers University. He has done numerous important contributions bridging mathematics and physics, and in his words will be bridging mathematical physics to physical mathematics. He has awarded Dirac Prize in 2015 with Kitev and Reed on their contributions to the interdisciplinary fields, which introduce concept of a conformal field theory and the non-abelian quasi-particle statistics in condensed matter and application to quantum computation. And he also did a foundational work with Nati Cyber on CFT and category theory. And these are just the very beginning of his career, and he has too much works for me to summarize. Today, he will talk about his recent work on summing over Bordisms in QFT. And let me remind the audience, please feel free to interact with Greg if you find appropriate time you want to ask questions. you can raise your hand first, or you can just go directly. So that is directly welcome, Greg.
Thank you. Thank you, Juven. And thanks for the invitation to give this talk at, in quotes, the Harvard CMSA. So the title of my talk is Summing Over Bordisms in TQFT. And this is work I did with my graduate student, Anindya Banerjee, who will be a postdoc at Queen Mary in September. And let me begin with some motivation for this work. So there's a long-standing problem in quantum gravity. I don't know what quantum gravity is, but presumably quantum gravity has something to do with assigning probability amplitudes to summing as in a path integral over metrics on some space-time, possibly weighted with something like the Einstein-Hilbert action or some variation thereof. So if we sum over metrics, the problem is, if we sum over metrics, should we also sum over topologies? And in one of the best controlled examples of quantum gravity, the ADS-CFT correspondence, there is nice evidence that, yes, we should sum over topologies. So right at the beginning of the whole story, Witten wrote an important paper pointing out that the Hawking-Page transition between two different topologies of hyperbolic manifolds in 5 dimensions matched up beautifully and quantitatively with confinement-deconfinement transition in N=4 super Yang-Mills. One of my favorites is if you look at the Poincaré series for the elliptic genus of the K3 surface. That's a Jacobi form, so it has a Poincaré series or related to it a Rademacher expansion, and you can interpret that as a sum over topologies in a ADS3 dual. And then recently, there's been a great deal of activity and excitement centering around the page curve and the lack of information loss, and the arguments in that development are based on dominance of certain topologies related in geometries related to black holes, dominance of one topology over another, explaining the kink in the page curve. So, maybe I duplicated that slide. Okay, so, but then there are also puzzles. So if you have a hyperbolic manifold, it can have several connected components. And again, right at the beginning of the ADS-CFT correspondence, that was recognized as presenting some puzzles known as the factorization problems. That goes back to Yao and Witten and was also stressed by Maldacena and Mayos. So the point is, if you have several connected components of the boundary, then you have disconnected field theories. So shouldn't the partition function be just a product of those field theory partition functions? But that's not the case if you have a geometry that's connecting them. Now, related to this, in an important paper in 2019, Saad, Schenker, and Stanford identified the sum over topologies in a certain two-dimensional model of gravity with a matrix model. The matrix model then being interpreted as an ensemble average of one-dimensional quantum mechanical models. As that raises conceptual questions about whether string theory should be dual to an ensemble of QFTs. So motivated by these developments, 2 years ago, Don Maroff and Henry Maxfield considered a curious topological model of 2D gravity. And an essential part of their discussion involved summing over topologies with disconnected components. So my project with Anindya was motivated by the desire to understand this Maroff-Maxfield model in terms of standard TQFT terms, because their paper was not written in a way that would be accessible to, say, a mathematician that works on TQFT. And I will comment more on the Maroff-Maxfield model later in the talk. So let me begin. It's probably unnecessary, but let me begin with some reminders about topological quantum field theory. So let's begin with the proper definition of a Bordism. What is a Bordism? So let X in and X out be smooth compact manifolds of dimension d-1. Then a Bordism y from x in to x out is, first of all, a D-manifold y together with a disjoint decomposition of its boundary. Boundary in and boundary out need not be connected, but I decompose disjointly the boundary into something I call the in part and the out part. And then we also have to have diffeomorphisms, boundary of y in with x in and out with x out, and embeddings of collared neighborhoods of x in and x out into y, which reduce to the specified diffeomorphisms on the boundary. So that's what a Bordism really is. So for example, if xn is disjoint union of 3 points and x out is a disjoint union of 5 points, then here's a one-dimensional Bordism from x to y. It's an unoriented Bordism. And there are 105 such pictures like this, such Bordisms, but in fact, there are infinitely many Bordisms from x in to x out because we can always include disjoint unions with circles. And that still fits my definition. Now, Bordisms are morphisms in a category. And in this talk, we'll only be looking at the top 2 levels of the category. And a TQFT in this talk is a monoidal functor to the category of vector spaces over some field kappa. So the basic idea is that the vector space of states for a spatial manifold X is the value of that, functor on the spatial manifold X, such that if I have a disjoint union of spaces, I get the tensor product of the state spaces. And if I have a Bordism from x in to x out, then z of y is a linear transformation from the in-state space to the out-state space in such a way that if I compose Bordisms, I get the composition of the linear transformations. So for example, if I have a 2-dimensional example, and I have a Bordism from 3 ingoing circles to 2 outgoing circles, and if C denotes the Hilbert space of the state space of a single circle, then this Bordism would be associated with an amplitude or a linear transformation from C tensor cubed to C tensor squared. So now let's talk about the total amplitude and the summed amplitudes. So as I just stressed, we can have different Bordisms between a fixed x in and x out. So now supposing we're given a seed TQFT, call it Z, and then we'll define the summed amplitude to be the sum over all the Bordisms from x in to x out of Z of y, weighted by 1 over the order of the automorphism group of y, where the automorphism group is the group automorphisms of homeomorphism types that restricts to the identity on the boundary. Now, when I think it's very interesting, and some very smart people have emphasized this to me, like Maxim Kontsievich, that you might consider other ways of weighting by the automorphism group. So I'm going to do what's been done so far in the literature, what's typically done in string theory, in topological string theory, but I think this is one of the weak links in the whole story. It would be interesting to consider other ways of weighting by the automorphisms of y. Anyway, this is my definition, and at least formally, it's some linear transformation from the in space to the out space. So what are some questions we could ask about it? Well, does this sum exist? If it does, is it computable? If it's computable, does it have any interesting properties we can see? And can we extend it to the fully local, fully extended TQFT? So here's some answers. Well, yeah, it exists for 1 and 2 dimensions. And it does not exist for 3 and higher dimensions, at least not in the most naive sense. Is it computable? Yes, when it exists, at least in all examples I've looked at. From explicit computations, it has an interesting property, which I'll call the splitting property, which I'll be stressing throughout the talk. And well, since we can only go up to 2 dimensions, there isn't a whole lot of room for extension to the fully extended TQFT, but there is some content to that in 2 dimensions, and that's the extension to open closed TQFT. Okay, so now let me define what I mean by the total amplitude. So let's consider these summed amplitudes, summing over Bordisms, and put all the possible in and outgoing states together into one big space. And so we have one big linear transformation. And where does it go? It goes from the tensor algebra of the direct sum over smooth connected D-1 manifolds, considered up to diffeomorphism. And it's just a linear transformation on the tensor space of that vector space. That's a countable sum. There's a theorem that there's a countable number of smooth connected manifolds in any dimension up to diffeomorphism. So the vector space is well defined. Now, because we sum over Bordisms, the sum actually descends to a sum on the symmetric algebra of this sum over z of x. And I'll call this sum over z of x the symmetric algebra of the sum over z of x, the Fock space of the seed TQFT. So that's what we want to study. We want to study a bar, which is, at least formally, a linear transformation on the Fock space of the seed TQFT. So what's the splitting property? Well, for
Fock space?
Question?
Is there
Sorry?
a reason it is called a Fock space?
That sounds like nutty. Yeah, well, because as you'll see, it really can be given the structure of a Fock. It can be completed. It can be completed to be given the structure of a Fock space in the standard physics sense. And you'll see it. You'll see some examples of that when I come to explicit examples in 1 and 2 dimensions. Okay, so I think I won't answer the question more now because I think you're going to see very explicit examples.
Excuse me, Greg, I also have a question.
Yes.
When you mention dimensionality, you say D equal to 1 and 2, there's an answer, but D larger or equal to 3, there's no answer?
I'm going to explain that in great detail.
You explain.
At least in the most naive way of proceeding, the amplitude A bar here does not exist. It's infinite. It's irretrievably infinite. I'm going to explain all that. It's irretrievably infinite. You can't even use something like zeta function regularization for 3 and higher dimensions. And that's why I was stressing the importance of thinking out of the box a little bit about possible, well, I'll talk about other ways of proceeding when we get there, but that's much later. So let's try and understand 1 and 2. Yes, huge problems above 2 dimensions. Yes.
Let me make in short sentence, is that because we lack of understanding of 3 manifolds or above?
Yes. We'll come on to all that. Yes.
For 1 manifold, there's no problem.
Patience. Yes. Yeah. So what is the splitting property? For the ground field C, you can put an inner product structure on this Fock space of the seed TQFT, such that there exists another inner product space, which I'll call the splitting space, W, such that A bar is phi times phi star. Now, where phi is a linear transformation from the Fock space of Z to the splitting space W. Okay, now I'm doing something a little funny here. So let me remind you that the space of linear transformations from one vector space V1 to another V2, denoted Hom V1, V2, is isomorphic canonically to the dual space of V1, tensor the V2. But if you think about it along the right-hand side, then it makes more sense to compose linear transformations on the right, whereas we usually write composition of linear transformations, subsequent transformations going to the left. But the formulas just look nicer when you compose on the right. So that's just a little technical thing, but I hope it will help later. Okay, so this is the splitting property. So let me make some comments about it. First of all, it's not some obvious thing because A bar is positive definite. A bar need not be positive definite. I do worry that maybe it's some simple linear algebra fact that I've overlooked. But even if the existence is trivial, explicitly finding the splitting space and phi in examples seems to be slightly non-trivial in examples. The splitting space is not unique. I could take the splitting space. I could take a direct sum of copies of the same splitting space. I could take phi. And if I have a set of positive real numbers, I could replace phi by the square root of this p alpha times phi acting on the alphath copy. There might be a minimal splitting space, and I haven't really tried to make precise sense of that. I think that's an interesting open problem. Now, I like to think that in some sense, W is the Hilbert space of a dual quantum mechanical system to the quantum gravity theory. So it's a much more abstract kind of holographic duality than the one we're all used to, because this W is not associated with any asymptotic region of space-time or anything like that. It's just a quantum mechanical system where we can express the gravity amplitudes in terms of amplitudes in the quantum gravity system. And I'll say more about that in more concrete detail later. For those who know about—
What is time in this quantum mechanics?
What is time?
What is time?
The time has no obvious, well, time is defined by one parameter family of automorphisms. I mean, it depends how you formulate quantum mechanics, but I think the real answer to your question is that the time that I would associate with this dual quantum mechanical system is not in any obvious way related to the time, to the evolution of the quantum gravity system. So later when I show you the formulas for d equals 2, I'm going to be much more precise about what I mean by 0.5 here. And if you're not satisfied, please ask again. Now, for people who are familiar with the theory of completely positive maps, you might be reminded a little bit of the Stein-Spring theorem for Hilbert C-star algebras, that's a misprint. It should say for C-star algebras. And I found that interesting because a few years ago, I wrote a paper with a kind of generalization of quantum mechanics, but I didn't have a really good example. And to my surprise, some of the ideas from that paper actually come up kind of naturally in this context. So let's get concrete. Let's talk about a one-dimensional TQFT and summing over the Bordisms. So we're going to consider the one-dimensional unoriented case. And then what's the data that determines the field theory? Well, we have the space of states associated to a spatial manifold, which is d-1 zero-dimensional. So the basic case is the point. And so we have a vector space, V. And then we have this piece of data. We can take a Bordism from 2 points to the empty set. The Hilbert space associated to the empty set is the ground field. So this picture gives me a symmetric non-degenerate bilinear form from V tensor V to kappa. And that's it. That's all there is to it. That's the data of a one-dimensional unoriented TQFT. So what's the Fock space? Well, the Fock space here is just the standard symmetric algebra on V, which we might complete. And so now you see if V had a non-degenerate bilinear form, I could use that to try and define a Hilbert space structure. And now we're really talking about a Fock space in the physics sense. So now let's compute the summed amplitudes. So let's start with X in and X out being the empty set. And so what kind of Bordism can we have from the empty set to the empty set? Well, there's the closed circle. And so Z of the closed circle is just the dimension of V. And so now what's the full summed amplitude? Well, now we have disconnected Bordisms. So the only thing you can have, the only closed one manifold, which is a Bordism from the empty set to the empty set, is what? It's a disjoint union of n circles. The automorphism group for such a thing is the symmetric group. We divide by n factorial. And so we have z of s1 to the n over n factorial, and that's the exponential of the dimension of v. So that's easy enough. Now let's start adding in and outgoing points. So because we have this non-degenerate form, there are canonical isomorphisms from, which I'll call the B isomorphisms, from V to V dual and V dual to V. And you notice that applied to the amplitudes, say with n in ingoing points and n out outgoing points, you can use these isomorphisms to produce all the other ones with the same total number of points. So for example, if I have a transformation like this from V cubed to V cubed, then by applying B, that corresponds to one of those factors. That corresponds to adding this green U-shaped Bordism here, which converts it into an amplitude from 4 ingoing points to 2 outgoing points. Okay, so that means it really suffices to compute what I call the Hartle-Hawking vector, or if you prefer, the Hartle-Hawking covector. So what's the Hartle-Hawking vector? The Hartle-Hawking vector is the sum of nothing goes to something, or nothing goes to anything.
I had another question. I'm sorry that I'm
yes.
so full of
I
questions.
welcome questions. I welcome questions.
Usually you play this role, but since you cannot ask questions today, I will do that. So do you assume that when you connect the incoming and the outgoing points, there are no junctions in between?
Yes, I do. That's an excellent question.
So, for example, if we would like to think of ordinary quantum field theory as along the word line of the particles, then particles can't split and join.
Good. Excellent question. So, excellent question. So, in top, you could ask, why don't you see generalizations of topological field theory where we generalize from manifolds to various kinds of more singular spaces like CW complexes or something. And you see, imagine we introduced a Bordism that looked like a Y. That's what Nadi's saying. A Y is like an interaction where one particle splits into 2. Well, in topological field theory, the whole thing will collapse to utter trivialities. You won't get any interesting amplitudes at all if you have such Bordisms. So it's important in topological field theory to restrict to manifolds. Now, I was asked a good question the other day by Sheryar. Why not use orbifolds? And that's a good question. I haven't really thought about that. So it might be possible to admit to extend beyond manifolds and introduce some manifolds with certain kinds of singularities. I've certainly heard Mike Hopkins talk about generalizing Bordism categories by adding various kinds of singularities. So that can be done, but that has to be, it's a delicate thing. And you can't just introduce in this one-dimensional case a Y the way Nadi wanted to do. Now, what about the fact that we have particles with interactions? Well, those are not topological field theories. And then we have propagators and we have non-trivial factors associated with those. I think the main point is that we have propagators and things depend on length. And then of course we weight the interactions with various things, but it's outside the bounds of topological field theory. So,
Greg, it's still not clear to me. In three-dimensional TQFTs, one often considers defects which look like Y.
But those are defects. That's the extended.
Well, it's another object in the topological field theory.
That's true. Well, since okay, so in this one-dimensional case, I'd have to think if I could introduce defects in any interesting way. I kind of doubt it because they have to have positive codimensions. So there's not a whole lot of room for defects. But in 3 dimensions, well, as I'm going to explain later, that's what I was saying to Juven before, we can't really get started, at least from the top down in 3 dimensions. Now, it does raise an interesting question I've wondered about, which is, suppose you have a fully extended higher dimensional TQFT, maybe you could define something like summing over Bordisms from the bottom up to a certain level. And I haven't explored that. But anyway, yes, there are you can admit defects in 3 dimensions, which are non-manifolds, but that's, I think we should be talking about manifolds with corners. So let's debate that more later. What I can tell you for certain is if in 1 dimension, if I introduce a y, then everything collapses, and it's not an interesting theory. Okay, so now let's go back to what I was saying. So what I was saying is that you can use this B morphism, this isomorphism, to convert ingoing points to outgoing points. So you could imagine, and you don't lose any information about the amplitude really, because it's an isomorphism. So you could convert all the ingoing points to outgoing points or vice versa. So what that means is that it suffices to compute what I'll call the Hartle-Hawking vector or the Hartle-Hawking covector. So the Hartle-Hawking vector is the sum of nothing to something or anything. And mathematically, you embed kappa into the Fock space, and that's the 0th symmetric product. And then you act with the total amplitude. And so if you apply that to 1, the composition of those maps to 1, you get a vector in the Fock space. That's the Hartle-Hawking vector, mathematically. And then, of course, there's a dual vector, which is the sum of anything to nothing. So you take the total amplitude from the Fock space to the Fock space, and you project onto the if you like, the ground state, if you project onto the 0 particle state. So that defines the composition of those, defines a dual vector on the Fock space, which I'll call the Hartle-Hawking covector. So now let's compute. So let's look at the simplest example. Supposing the dimension of V is just 1, the ground field is C, and we have some non-degenerate bilinear form, so we can choose a vector whose norm squared is 1. So here's the formula for the Hartle-Hawking covector. So you see those V duals to the 2n, so you think of those as eating up ingoing vectors. So look at so what I'm saying is you have to have an even number of points, because remember, we're going to the empty set in the Hartle-Hawking covector. And so what is this combinatorial factor, 2n factorial over n factorial to the n? Well, supposing I have 4 ingoing points, well, there's one Bordism to the empty set, and there's another one, and there's another one. And you all recognize this from Wick's theorem. You know, this is the number of ways of pairing up 2n points into collections of pairs. So that's the formula for the Hartle-Hawking covector. The exponential of 1, that takes care of the Bordisms, including the disjoint circles in the Bordisms. Okay, so now we apply this U-shaped morphism to convert ingoing points to outgoing points. So there's the general answer. And yes, that's in the symmetric algebra of V dual, tensor to the symmetric algebra of V, and that's isomorphic to the linear transformations on the Fock space of V. So now let's look at the splitting. Well, I just invoked Wick's theorem, and indeed, we learn this combinatorial fact in the context of Wick's theorem, where part of the story is that combinatorial factor is a Gaussian integral over the real line of h to the 2n e to the minus half h squared. So introduce psi n in the L2 space of the real numbers. There's your splitting space, W, given by h to the n e to the minus 4th h squared. And it has the property that the inner product of psi n and psi m is 0 if n plus m is odd. And it's the desired combinatorial factor if the sum is even. So here's phi, the splitting map. So it's the sum over n of V dual to the n tensor psi m. So if you imagine taking phi star and pairing the psi n and the psi m star in the middle, then you get exactly the right combinatorial factor with the right constraint that n plus m is even. So there's your splitting formula. So this all generalizes, of course, to general vector spaces dimension bigger than 1 and general bilinear forms. And one way of summarizing the full set of amplitudes is this. we could take the Hartle-Hawking covector, we could take a vector v, and we could take e to the v, which is formally an element of the symmetric algebra. It's 1 plus v tensor v over 2 factorial, and so on. And so I can apply the Hartle-Hawking covector to that. And here's the general formula for any vector space V with any bilinear form. And that really captures the whole information because the Hartle-Hawking covector is multilinear and totally symmetric. So it's completely determined by its values on the diagonal. Now, in the literature, Maroff, Maxfield, and a follow-up paper by Gardner-Megas, they didn't look at the d equals 1 case, but in the d equals 2 case, they have analogous formulas where they have the right-hand side, but they don't tell you the left-hand side. So what we're contributing here, at least part of what we're contributing here, is an interpretation of what is the left-hand side. Okay, now let's talk about the two-dimensional case. So there are many different kinds of two-dimensional TQFTs. We could have closed and semi-simple. And there we have a complete story. We could have open, closed, and semi-simple. We have a complete story. You could have closed and non-semi-simple. There we have only examples. We can't give you the complete general answer there. And open, closed, and non-semi-simple, well, there are conceptual problems with what that even means. You see, if you have a fully extended TQFT, then actually there's a theorem of the mathematicians prove that it has to be semi-simple. On the other hand, it's pretty obvious that there are examples of open, closed, non-semi-simple TQFTs, and Graham Siegel and I gave examples with boundary conditions. So they exist, but it's really not completely clear what the full set of boundary conditions is for a non-semi-simple Frobenius algebra. Anyway, let's start with the simplest case, closed and semi-simple. So it's a fact going back to geological times that the theory is completely determined by commutative Frobenius algebra. That's the space of states on the circle. So the Frobenius structure, the trace, is given by the functor applied to the disk, where you think of the disk as a Bordism from an ingoing circle to the empty set. And the multiplication is given by the pair of pants, etc. And then you can prove that if you multiply and then take the trace, that's a symmetric non-degenerate form, and that's the definition of a Frobenius algebra. And I'll come to the open closed case later. So let's now simplify it to the case where Z of S1 is semi-simple. In the semi-simple case, C can be written as a direct sum, orthogonal sum of one-dimensional Frobenius algebras. So these are generated by idempotents, epsilon sub x, which satisfy this property, that epsilon x times epsilon y is delta xy times epsilon x. And the entire data of the Frobenius algebra then is given by the trace on epsilon x. I'll call it theta x, and it's an invertible element in the ground field. So there's a nice interpretation, physics interpretation, which is we're doing 2D topological string theory with a target space, which is just a finite union of points. Mathematically, it's the spectrum of the Frobenius algebra. And what is the theta x? It's basically the string coupling constant, the dilaton, in this component, in the component of the universe. So the universe is just a finite disjoint union of points. So it has connected components. And in each component, you have a string coupling. That's what theta x is. Okay, now let's calculate the total amplitude. So first, let's start with the empty set to the empty set. So that's the exponential of the sum over the connected Riemann surfaces of genus G. So y0 is the circle, y1 is the torus, and so on. And now that's a geometric sum where we have a geometric sum given by the handle adding element. So the handle adding element is that element in the Frobenius algebra given by the one-hole torus with one outgoing circle. And then in the semi-simple case, that simplifies to a sum over the universes of lambda x, where lambda x is just the geometric sum of the string coupling. So it's that simple, and everybody knew that for a long time. Now let's it gets a little more interesting now when we think about two ingoing circles and two ingoing circles and no outgoing circles. So let's apply that to two vectors in our Frobenius algebra. What do we get? So for simplicity, let's take one-dimensional Frobenius algebra. So it's generated by a single idempotent, epsilon. And so phi1 and phi2 have to be proportional to epsilon. Take z1 and z2 to be complex numbers, if you like. And now let's think about the Bordisms from two circles to the empty set with just one connected component. What do they look like? Well, you can have a tube bent around, and then you can start adding handles to it. And that's all you can do. So what you get is z1 times z2 times the geometric sum of the string coupling. And similarly, if I have Bordisms with one connected component and n ingoing circles, I just multiply up the z's and I have the sum of the geometric sum of the string coupling, lambda. But now, if we have two ingoing circles, we can also have two connected components, like two disks, or two disks where I've added an arbitrary number of handles to either of the disks. So then the amplitude is z1 times z2 times lambda squared. For each of these disks, I have the geometric sum of the string coupling, so I get lambda squared. So altogether, the amplitude from 2 to nothing is z1, z2, e to the lambda. The e to the lambda is for the disjoint closed surfaces. And then we have lambda plus lambda squared. And Maroff and Maxfield recognized that that's not random. That's something called the second Bell polynomial. And I had to look it up. So let me tell you what the Bell polynomials are. So the Bell polynomial, Bn of x1 through xn, is a polynomial that counts the number of ways a set of n elements can be partitioned in such a way that the coefficient of x1 to the k1 times x2 to the k2 and so on will count the number of disjoint decompositions where there are k1 subsets of cardinality 1, k2 subsets of cardinality 2, and so on. And so it's relevant to us. Okay, so let me just define Bn of lambda, which is Bn where all of the xi's are put equal to lambda. And why is that relevant to us? Consider a Bordism of n ingoing circles to nothing. And just imagine one. And now imagine dividing it into its connected components. So there'll be different connected components. And if I have a connected component with j circles, well, that will contribute when I sum over the handles just to a single factor of lambda, a single geometric sum of the string coupling. So if I have kj such connected components, I'll get a lambda to the kj. So the upshot is, and then I sum over all the combinatorical ways of dividing the ingoing circles that way. So the upshot is that the Hartle-Hawking covector is e to the lambda times Bn of lambda times the dual vector that eats up ingoing vectors, dual vector to the nth power. And now applying the B morphism, there's the general amplitude. So there it is. That's the, excuse me, that's the general amplitude for ni ingoing circles, n outgoing circles, one-dimensional Frobenius algebra. That's the answer.
Greg,
now, yes,
I have a question. This is Shuhan.
Hi, Shuhan.
Hi. If I understand correctly, this example is a trivial to the TQFT where the only local operator is the identity operator. Is that right?
It's the simplest case.
Right. So in a trivial,
I wouldn't quite say it's trivial. I mean, there's still theta.
That's exactly the question I would like to ask.
Yeah.
So the theta, I think from the maybe a more physical term, is just the Euler counter term of the TQFT. Am I correct? It's the Euler counter term.
Yeah. So right. So Shuheng, if I compute the partition function on a closed Riemann surface of genus G, the answer is theta to
exactly
1/2 the Euler character.
Right. But then my question is, from the quantum field theory point of view, we usually view the Euler counter term, as some kind of, it's a scheme, it's a counter term. So the interesting physical observable should be independent of those counter term. So how should I think about the theta dependence here? Usually we don't care too much about quantities that depends on counter term.
I disagree with, I mean, I know the point of view that you're taking, but I disagree with that in the context of TQFT. I mean, you can have non-trivial invertible. I would say this is a non-trivial invertible. It's not a very difficult or subtle TQFT. It's just it's an invertible theory, which is an Euler character, some constant to the Euler character. That's the theory we're starting with. We will generalize, but that's the theory we're starting with.
Okay.
That's a TQFT. I mean, I can't really say much more. I would not say it's a trivial TQFT. The trivial TQFT would have partition function 1.
Right, I understand. So sometimes when we work with quantum field theory, we work modulo the counter term or invertible field theory. But here, I guess in this context, you do want to keep track of those dependence.
That's right. We're doing a little baby. What we're doing here, Shuheng, is a baby version of quantum gravity. So we're taking the simplest possible TQFT, and the main interest here is in the sum over the topologies and how that affects the fit, the maps from the ingoing space to the outgoing space.
Mm-hmm. Okay, got it. Thank you.
And now it's not at all hard to generalize. Well, okay. So I'll be talking about generalizations, and you'll decide if they're non-trivial or not.
Mm-hmm.
So this is
interrupt quickly. Sorry. So I just wanted to ask Shuheng why he said that there are, or even you, like why there are no local operators, non-trivial, in the
because the dimension. I mean, we can identify the operators with the state space. The state space is one-dimensional. So
your Z of S1, your commutative Frobenius algebra.
Z of S1 is the commutative Frobenius algebra. It's one-dimensional. It's the complex numbers.
Oh, okay. So I somehow missed that assumption.
And epsilon is the idempotent. So epsilon squared is 1.
Okay, thanks.
All right, I should say Z of S1 is isomorphic to the complex numbers, and epsilon is the thing that gives you that isomorphism.
Okay.
All right, so now that the e to the lambda bn of lambda has a very nice series expansion, which I've written here, lambda to the d over d factorial times d to the n, sum from d equals 0 to n. This formula I will come back to and was also used extensively in the Marolf-Maxfield paper, and I will comment on their use later. All right, so here again, this is the formula for the total amplitude, ni ingoing circles and outgoing circles. We now apply this nice identity for the Bell polynomials, and we substitute it, and now you start to see, all I've done is substitute that formula, and now you start to see the factorization, because stuff that depends on ni can go to the left, stuff that depends on n out, the number of outgoing circles, goes to the right, and we can think of this sum over d as some kind of sum over intermediate states. So now let me make that precise. So because of the Frobenius structure, we have a canonical sesquilinear form where the adjoint of epsilon is theta times epsilon dual. And so now in this case, the splitting space will be the same as the Fock space of C. And then for theta real, but not necessarily positive, we can write A bar as phi dual, phi dagger. I wanted to make a phi dagger. I wanted to make a dagger instead of star, but PowerPoint wouldn't let me. So it has to be star. So phi star means phi adjoint with respect to the sesquilinear form. Anyway, phi is given by this formula here. And now if you look at this, look at the second factor, you have epsilon to the d. And now imagine taking phi star, then you'll get an epsilon to the epsilon star to the d on the left. You contract those two and you get that sum over d in the middle. So there's the splitting formula. So let me make some comments about this. First of all, the amplitudes that I've shown you can be invariant under the action of a global, of a non-trivial global symmetry group. So in the one-dimensional case, we have the orthogonal group of the bilinear form. In the two-dimensional case, the Frobenius structure could have automorphisms. I could have several components of the universe with the same string coupling. Imagine I have n components of the universe with the same string coupling. Well, then there would be a global symmetry that a symmetric group, global symmetry, that permutes those points. So, you know, it's a standard thing in quantum gravity that there are no global symmetries. But those arguments use non-trivial things like black holes or properties of anti-de Sitter space that are not present in this case. So in this very baby model of quantum gravity, it's worth observing that there's no problem with global symmetries. And by the same token, the amplitudes can depend on continuous parameters. Now, something that I found surprising is the following. If I take the Hartle-Hawking vector, that was the sum of nothing to anything, and the Hartle-Hawking covector, which is the sum of anything to nothing, those are vectors and dual vectors, and I can contract them. Turns out that that's not the same as the vacuum to vacuum amplitude, the empty set to empty set amplitude. And in fact, the contraction of the Hartle-Hawking vector and covector is divergent. So it's only a formal element of the Fock space. It's not a normalizable element, unless we start to change the way we divide by the automorphism group. So I haven't explored that very systematically, but it's something one could do. If you really want this contraction to be finite, you would have to change the way you sum over the divide by the automorphism group. Finally, there's a relation to coherent states where we're going to get closer to things that Maroff and Maxfield did. So let's take the standard bosonic oscillator, and it has a standard representation where the vacuum line is annihilated by A, etc. And then the creation operator acts on that, a choice of vacuum. Let's call that normalized vector D, and that would correspond to epsilon to the D in our symmetric algebra. And we can define I said we can define a sesquilinear form. So for an orthonormal basis, it's epsilon over the square root of theta to the D. So now consider the coherent state associated with the square root of lambda and consider the number operator, A star A. Then here's a nice way of thinking about the Bell polynomials. The Bell polynomials are the expectation values of the nth power of the number operator in a coherent state. And from that, you get the formula I flashed before. Well, never mind. You get the formula, the power series I flashed before rather easily. I should have put that here. Okay, so now let's do the following. Let's define an operator from the splitting space, which in our case is the same. In this two-dimensional closed TQFT is the same as the Fock space of C. But it's conceptually different, so I'm going to denote it by blue. So Z, this is the universe annihilating operator. It goes from the splitting space to the dual of C, tensor to the splitting space, and it takes D to a multiple of epsilon dual times D. And Z creation goes from the dual of the splitting space to the dual of the splitting space tensor C, and it takes the bra vector D to bra vector D tensor something multiplying epsilon. So then here's a formula for the total amplitude. It's an expectation value in the coherent state of 1 over 1 minus Z creation times 1 over 1 minus Z annihilation. So the blue stuff is getting traced out and the red stuff remains, and the red stuff is in S star C dual tensor S star C, which is linear transformations on the Fock space of C. So this is what I meant before when I said that the splitting space is like a holographically dual quantum mechanical system. So I'm taking expectation values in this blue quantum mechanical system and producing operators, the amplitudes of the quantum gravity. So Nadi asked me, where is time? So it's kind of hard to answer that. I mean, if I have a quantum mechanic, if I have formulated a quantum mechanics in terms of a Hilbert space and operator algebra in the Hilbert space, well, what is time? Time is just an automorphism of the operator algebra, a one parameter family of automorphisms. The time of this blue quantum mechanics has no obvious relation, at least not obvious to me, to any kind of time in the red quantum gravity. Those are just words, but the formulas here are precise. And you can read into it what you want, but that's the way I see it. All right, let's go on to the open-closed case.
Great, naive question.
Yes.
So maybe two questions. First is that are these discussions somehow change if we want to specify certain structure on the manifold, and also whether these has some relation?
Yeah. That was going to be in my open problems list, but I can say it now. So yes, there are various extensions. At the very end, I would list ways one could extend the current work. One thing that you can extend, which we did in our paper, which is completely straightforward, is to go from the one-dimensional semisimple algebra to the general semisimple algebra. So you just have several universes, not a big deal. Another thing you could do is you could put various tangential structures on your Bordisms. So Nadi wanted to make it not a manifold. And then my answer was then things will collapse. But you could, of course, put in orientate. Well, here we're doing the oriented case in 2 dimensions, but I could consider the unoriented case, and then I would have to work with crosscaps and Klein bottles and things like that. Or you could put spin structures or pin structures or other tangential structures. And yes.
And another question is that it seems like when you say sum over TQFT in your talk, the TQFT here was placed perhaps in the one higher dimensional manifold than the usual people classify the Bordism group, which is, let's say, n-dimensional manifold connect cobordent by another n-dimensional manifold by an n+1 dimensional manifold. It seems like the TQFT or sum over is the n+1 dimensional manifold here. So
let me answer that.
Yeah.
So first of all, I'm not summing over TQFTs. At the very beginning, I was saying, let's take a seed TQFT. So part of the data of the construction is I start with a single TQFT, curly Z. Then what am I summing over? I'm summing over Bordisms from a fixed ingoing space to a fixed outgoing space. That's what we're talking about. That's what A bar is. So the only thing we're summing over is Bordisms for a fixed TQFT. Okay. Now, I'm not playing any of that game that you're talking about where we express, we have an anomaly field theory 1 dimension higher. I'm not doing anything related to that here. That's a beautiful topic, but that's not what I'm doing here.
Yes, thanks.
Okay. All right, so let's talk about the 2-dimensional open closed case. This is a little more non-trivial. And I'm going to talk about the oriented semi-simple examples. So now the in and outgoing manifolds can be disjoint unions of circles and oriented intervals. The intervals themselves should be thought of as one morphisms in a category. So we have now manifolds with corners. Here's an ingoing or outgoing interval. And at the ends of the interval, we have to put boundary conditions. And the boundary conditions are objects in a category of boundary conditions. And the functor, the topological field theory functor applied to this interval labeled by boundary conditions A and B, which is the interval is oriented, is the Hom space from A to B, which in physics language is the open string space for the oriented open strings from boundary condition A to B. So OAB I think of in terms of the open string state space. So now our morphisms, our 2 morphisms are really 2 morphisms in a 2 category. And here's a typical picture of the kind of morphism we would have. So here we have a Bordism from 2 ingoing intervals and 1 ingoing circle to just a single outgoing interval. And now you see the boundary of this 2-manifold Y is divided up into 3 kinds of parts. There's the ingoing boundary in red, the outgoing boundary in purple, and then the endpoints of the intervals have to get connected up by a boundary that that carries a boundary condition. And those are the dotted green lines. And I'll call those constrained boundaries. That's what Graham Siegel and I call them. Now we can also have a different kind of, we can also have closed constrained boundaries, which carry the label of a boundary condition. So there are really three conceptually distinct kind of boundaries here. There are the in and outgoing circles and intervals. So here we're thinking physics. We're thinking physics is about, having something in the past and going to something in the future. And we know what it is the in and outgoing circles and intervals. Then there are also the constrained boundaries that connect the in and outgoing endpoints to the in and or outgoing endpoints of intervals. So those are the dashed lines that you see in this picture. And then a third kind of boundary you can have is a closed constrained boundary. And I stress this might seem trivial to you, but I stress this because one problem I have when reading the quantum gravity literature is they're not careful about the distinctions between these different kinds of boundaries. So for example, let me make a side remark here on the Maroff-Maxfield model. So Maroff-Maxfield defined their model by summing over surfaces with boundary with a weighting factor, which is S naught times the Euler character. Notice Shuheng, S naught times the Euler character, plus S boundary, another parameter, times the number of boundary components of Y. But many people, quite correctly, objected when their paper came out that, wait a second, that's not a local term in the action. So that doesn't look like a good model, even a baby model of physics. The resolution is that when one is careful about the interpretations of the circles, okay, S boundary is just a parameter. It need not be interpreted as part of the action. There are different interpretations that depend on whether we take the boundary circles to be in or outgoing or constrained boundaries. So in our language, Maroff and Maxfield considered the dimension C equals 1 case, and the generalization of their story in their language was done by Gardner and Megas. And here's the kind of formula that you'll find. Well, I'm getting ahead of myself. So now if we evaluate the Hartle-Hawking covector on the exponentiated diagonal with some parameter u tilde times the idempotent epsilon, then using the rules I just showed you, it's rather easy to show that this is the exponential of lambda, the geometric sum of string coupling, times e to the u tilde. Well, you'll find the right-hand side of this equation in the Maroff-Maxfield paper. And in order to convert our expression to theirs, u tilde has to be identified with u Maroff-Maxfield times e to the s boundary minus s0. So you see, e to the s boundary is just a parameter multiplying the ingoing vector. It's not a term in the action. Or if we considered their boundaries to be closed constrained boundaries, then e to the s boundary is just a fugacity for how you're inserting those closed constrained boundaries. It's not a term in the action. Okay. So after that little homily, let's get back to the splitting formula for the open-closed case. So let's take the very simplest case we can do. And in our paper, we relax all these conditions. So let's take the dimension C to be 1. All the constrained boundaries are labeled with a single boundary condition A. So now the open string space from A to A is an algebra, the open string algebra, OAA. We'll have no closed constrained boundaries. We'll talk about those again in a moment. And all of the in and outgoing manifolds will just be intervals with that boundary condition A. Okay, no ingoing or outgoing circles. This is just to simplify everything. Okay, so in order to write down the amplitudes, you have to take a square root of theta. And physically, you have to introduce the open string coupling, which is mu inverse. So now, for the splitting formula to work, you need to take mu to be real. So theta has to be positive in this case. And then, yes, we have the splitting formula. And what is phi? Well, phi goes from the symmetric algebra on the open string algebra to an L2 space of some vector space. What is this vector space? Well, the open string algebra is a priori just some finite dimensional C-star algebra. But the Carty condition implies that, in fact, it's not a direct sum of matrix algebra, it's a single full matrix algebra. So that defines an integer n sub a. And so E sub n sub a is the vector space of NA by NA Hermitian matrices. Okay, So that's what phi looks like. So let me write a formula for phi. So it looks like this. It's the sum over little n. That's the number of ingoing intervals. For each interval, we have to sum over I1, J1, I2, J2. The i's and j's run from 1 to the capital NA. Then we have the product over the intervals of EIA, JA dual, where here EIJ is a basis for my open string algebra, and EIJ dual is the dual basis. And then we multiply that with a matrix model type integral. So on the very far right, you see a bra vector, H. That's the element of the L. That's like the plane wave in the L2 space. And then what's the matrix model potential? The matrix model potential is a Laplace transform of the exponential of lambda over the determinant of 1 minus s to the open string coupling. So yeah, a little strange, but that's what it is. A corollary of this is the value of the Hartle-Hawking covector on the exponentiated diagonal, which is exponential of lambda over the determinant of 1 minus t to the open string coupling. And the right-hand side is something you'll find in the Gardner-Megas paper. All right. Let's see, how am I doing for time? I think I've gone for 60 minutes. Juven, help me. So it's supposed to an hour and a half?
Yes, you still have time.
All
30 minutes more.
All right.
You can take as much time as you want.
All right. I don't know if there are any mathematicians in the audience here. So, but in case there are, let me make the following remark. Among the amplitudes, we certainly have an amplitude from n ingoing intervals to 1 outgoing interval. And so that's mathematically a n linear map from the nth symmetric product of the open string algebra to the open string algebra. So that gives a series of n linear multiplications. Now, when I realized that, I said, oh, ho, there's some role here for, I don't know, Hochschild cohomology or A infinity or L infinity, and that's all wrong. None of that works. And so here are the first few multiplications. So in the A infinity language, this is a multiplication with curvature. So there's an M0 term. Then there's an M1 term. So M1 of T, it has a piece proportional to the identity matrix times the trace of T, and then a piece proportional to T. And here's M2, and it's all looking very terribly complicated. The thing I want to, call your attention to is the very last term on the formula for M2, where you see the Jordan algebra structure on matrices. So the anti-commutator of T1 with T2. Well, it has to be something like that because it's symmetric. And well, we don't know what to do with that. So I'm just putting it out there. It's a funny mathematical structure. I don't know if there's a homotopical version of Jordan algebras. I've never seen that. So it's pretty complicated, as you see, but it would be nice to know conceptually what these multiplications are. Okay, let me talk a little bit about the case of closed constrained boundaries and the ensemble interpretation. So the aim of the Maxfield paper, as far as I understood it, was they were trying to give an interpretation of the two-dimensional topological model of quantum gravity that we've been talking about in terms of an ensemble average of 1D models. Of course, they were motivated by the things I mentioned at the very beginning of the talk. So how can we understand that in the present language? Well, we could consider the sum over Bordisms from the empty set to the empty set with L constrained boundaries of type A. And so we would say sum over genus like this, and here's the case L equals 2. So we have two closed constrained boundaries. These are not ingoing, they're not outgoing, they're just boundary conditions. And we can add arbitrary genus. And then of course we have all the disconnected cousins of this. So we have to sum over all that. And what do we get? Well, using exactly the same kind of reasoning that I've explained to you before, I won't go through details, you can see that that sum of amplitudes divided by the vacuum-to-vacuum amplitude is now the Elf Bell polynomial. I'm getting a lot of junk spam phone calls. Is the Bell polynomial from x1 to xl, where xj is the Frobenius trace of 1 over 1 minus the handle adding operator times the boundary state to the jth power. This is a formula, by the way, that works in the non-semisimple as well as the semisimple case. What is the boundary state? Well, I take the open string, I consider the following morphism from an interval to a circle. So it's an open to closed string transition. And it's the simplest possible one. And I consider applying this morphism to the identity element in the open string algebra, and I get a state in the closed string space called the boundary state. So xj is expressed in terms of the boundary state. In the very simple case where the dimension of C is 1, then the boundary state, of course, is proportional to the idempotent, and the proportionality constant. Well, if OAA is NA by NA matrices, then the proportionality constant is NA divided by mu. Okay, so what that means, and now if we use the formula that I showed before for the series expansion of the Bell polynomials, then we get 1 over mu to the L times e to the minus lambda, lambda to the d over d factorial times dna to the nth power. And now you can interpret that as up to this power of the string coupling, you can interpret that as an ensemble average of partition functions of one-dimensional TQFT to the nth power, where z here is a stochastic variable on an ensemble E of 1D oriented TQFTs labeled by non-negative integers. So I'll call them z sub d. And the probability of that TQFT z sub d is a Poisson distribution. I'm assuming lambda is positive. And then in that case, the probability is the Poisson distribution, and my ensemble, here I'm defining the ensemble precisely, says that the Hilbert space of states for the dth TQFT is D times NA. So it actually depends on NA. So that's an ensemble interpretation. I think that's the spirit of what Maroff and Maxfield were doing, except they were sort of mixing up ingoing states with constrained boundaries. Now, it would be useful to give an ensemble interpretation to the full set of open and closed amplitudes. I mean, this is just one thing, the vacuum-to-vacuum amplitude. What if I take closed constrained boundaries with ingoing states and outgoing states? I don't know if that can be given an ensemble interpretation. It does suggest an interesting thing, which is that in TQFT, you can have any symmetric monoidal category as the target category. So perhaps we should be thinking of TQFTs where we have a category of finite dimensional vector bundles over measure spaces as a way to model ensemble averages of field theories. So I'm just throwing that idea out there. It's an idea that might be interesting to pursue. Okay.
Greg, before you move to higher dimensions,
yes,
maybe you mentioned, I have a question about, which is related to global symmetries in quantum gravity.
Yes.
So you talk about boundary conditions and all that. Did you talk about line operators, topological line operators?
No, I haven't discussed that. Discussed that.
So I guess in the math language, that would be generalizing this formalism to G equivariant TQFT.
Well, right? I mean, sorry, Shuhen. I've discussed that a little bit.
Okay.
That's but not completely. I haven't discussed interfaces, but I have discussed boundary conditions.
Yes, but the more general interfaces.
But I have not discussed the interfaces. That's an excellent point. Excellent point. It would be interesting to do that.
But do you think there's a generalization to the more general?
I don't know. I mean, we have to decide how we would sum over topologies.
Right.
When we include the interfaces. I mean, it's easy enough when we have boundaries, right?
Yes.
Okay. So, and that's what I did that with Anindya, but it's an extremely nice point. What about including interfaces? No, we didn't do that. We didn't do that.
And that would directly address the question about whether it makes sense to talk about global symmetries in such models where topology is being sung over, right? Because global symmetries are implemented by such.
Yes. Yeah. Nice. Yes, I understand where you're coming from.
Okay.
Yeah. I mean, I showed in the purely closed case that you can have global symmetries, but indeed, well, this is actually related to something. This is related, not exactly, but it is related to something on my list of future directions. But on my list of future directions, I actually missed this one. So that's a good point.
Okay, thank you.
Okay, let's come to d equals 3 and higher. So I mean, this to me is the main open problem in this subject. And as Juven alluded to, the first thing that hits you in the face is that the classification of manifolds, to put it mildly, is much more difficult. So, what's involved here? Supposing we're in 3 dimensions and we just want to do the very simplest thing. This is the trivial part of the story, where we go from the empty set to the empty set. Well, now we have to sum over closed connected 3 manifolds, weighting it by the value of the topological quantum field theory on the 3 manifold Y. Well, people write whole papers, evaluating Z of Y for specific 3 manifolds. So it seems like a tall order. And it's even worse because you see that sum includes things like Y is S1 times a Riemann surface of genus G, in which case we do know the answer. Z of Y is just the dimension of the state space of Riemann surface of genus G. And for the standard fully local TQFTs that we know and love, like Chern-Simons-Witten theory, the dimension of Z of G, of sigma G, grows with G. And I would say that the sum is irretrievably divergent. I mean, for example, what I mean by irretrievably divergent is you might think, oh, well, maybe there's some clever regularization and analytic continuation. But think about the case of an invertible theory. Then you're summing 1, and an infinite sum of 1s is the zeta function on its pole, so it's divergent. So that made me ask the following question: could we have an interesting TQFT where the dimension of the state space is 0 for sufficiently large G? And after talking around with some people, Sergei Kukov made an excellent point to me. He said, no, because look, you could cut along the boundary of a handle body for any genus G. So, for any 3 manifold, you take any point, you take a little ball around that point, and you can insert in that ball a handle body of any genus. So it's an interesting point I hadn't realized before, that if the Hilbert space is 0 for any genus, then all of the amplitudes in your TQFT vanish. So that option is closed. So one idea that would be fun to explore maybe is to modify the domain or the codomain categories to produce interesting examples. Possibly we should think about different ways of weighting by the automorphism group. There are various ideas that come out of non-compact 3-dimensional Chern-Simons theory that might be useful here. So Anderson and Kashayev found that they could not really define a TQFT for non-compact 3-dimensional Chern-Simons, and they had to retreat a little bit and introduce something called categoids. I don't know if that's useful to us here, but we need some ideas to go on to beyond to go from 3 dimensions and higher. Now, you might think that there's something like, well, let's just sum over handle bodies. Why not just sum over handle bodies? That's actually been proposed in many discussions of 3-dimensional quantum gravity. That's a problem, because you see, in topological quantum field theory, you need to have gluing, and you need to be able to glue with arbitrary diffeomorphisms. But then the game's over, because if you have a handle body, if you're allowing handle bodies, then by Heegard decomposition, you can get any 3 manifold. So there's no such subcategory. So it's not obvious. So this is where we are on that. Okay. Let me summarize and mention some open problems, and we'll have some time for questions. So for suitable parameters, our TQFT, the total amplitude has a splitting formula where phi goes from the Fock space of Z to some inner product space W, the splitting space. And in the talk, I showed you lots of formulas they were all in the semisimple case, and Anindya and I worked out some examples for non-semisimple closed two-dimensional TQFTs. And it's not obvious from the formulas, but the splitting does persist. Now, various extensions. Well, I've gotten some of these, suggestions about this during questions in the talk. So the general non-semisimple case is something I don't know, and especially the open closed case looks, well, they're important conceptual questions there about what you're even talking about. As we discussed, other tangential structures, unorientable, spin, pin, whatever. Now, something related, but not exactly the same as what Shuheng was mentioning is G equivariant theories. That's an interesting direction for generalization. Closely related to that is you could relax topological field theory just a little bit by allowing total area dependence, as in 2D Yang-Mills with non-trivial area dependence. And I have managed to check that the summed amplitudes do appear to exist, and I even have formulas if someone wants to see them. So the summed amplitudes appear to exist, and whether there's a splitting formula or not, I don't know. Now, an obvious question is, what about topological string theory? So if I have topological string theory with some Calabi-Yau as the target space, we would be, the topological string theory should be giving us some linear transformation of the Fock space of the quantum cohomology of the Calabi-Yau. And I guess it ought to be possible to check if there's a splitting formula, at least in perturbation theory. Now, something I need to say is that I do worry a little bit that I might be telling you something completely trivial. I wonder if the splitting formula is deep or if it's just a trivial consequence of linear algebra. And so what I have in mind when I say that is the following. The rough idea is that the total amplitude is, in some sense, should be symmetric under exchange of all the ingoing boundaries for all the outgoing boundaries. Well, in finite dimensions, if I have a symmetric finite dimensional complex matrix, then I can always write it as phi transpose for some phi. Now, I haven't been able to take that intuition and turn it into an honest argument that I actually believe. So I don't really know if it's a trivial consequence of linear algebra, but maybe I'm just missing something. If it doesn't just follow by linear algebra, then it would be really nice to know an a priori reason why it should hold. So for example, one of the reasons I think it might not be trivial is I had to say things like theta is real or mu is real and theta is positive. And if you don't have that, then you get phases that kind of mess up the splitting formula as far as I can tell. So I'm not sure it's trivial, but maybe it is. If it isn't trivial, it would be nice to have a good reason why it's true when it's true. Anindya and I just checked it case by case. We looked at one-dimensional theories, we looked at two-dimensional oriented closed theories, and so on. And we just check it case by case. So if it's deep, there should be a reason why it's true. A splitting formula for JT gravity could have very interesting implications for the ongoing discussion about the role of ensemble averages in ADS-CFT. It was just a paper on the arXiv yesterday from Stanford that looks relevant to that. And of course, what to do about 3 dimensions and higher. So I've gone on for quite a while. Thanks for the questions and thanks for your attention.
Thank you, Greg, for the wonderful lecture. And any question from the audience or comments?
Yeah, please. I have a question. So the discussion so far has been for TQFTs, but you mentioned there could be a generalization to 2D Yang-Mills. But what if you really try to do this with the JT gravity amplitudes? Do the sums make sense? And do you have the same mathematical structure?
I have not seriously tried to do this in JT gravity. So it's on my list of open problems, but it's not something that I've seriously tried to do. So I can't answer that.
I see, thank you.
So one thing I was wondering about is what kind of thing would you get if you applied some of this to the A model? For example, one interesting thing would be to, so you mentioned this OAA. So if I take like some Lagrangian boundary condition, shouldn't your formulas imply that some new n-ary maps on HOM LL?
I guess so. Yeah.
Okay.
From summing over Bordisms. Yeah.
Mm-hmm. Okay. I wonder what that geometric.
Yeah, I don't know. I don't know. Yeah.
I have a follow-up question on the G equivariant cases.
Yeah.
So let's say we just do the closed case, put the open case aside. Then what would the sum amplitudes, how would the sum amplitudes depend on the topological lines? I guess it only makes sense to put the lines around the in or out boundaries, but not anywhere in the intermediate.
That's what I'm worried about. If I put them inside, what is exactly the sum over topologies means?
Right. And I thought, and that's usually the way I argue there's no global symmetry in quantum gravity.
Oh, I see.
because global symmetry is defined in terms of all this topological line or more general topological operators.
Well, I would say that's one way to implement it, but Shuheng, I mean, I gave you examples where there's a global symmetry.
Yeah, can you say a little bit more on that example?
Sure,
I didn't quite get the example.
Oh, okay, let me stress that. So, sure. I think the simplest case, yeah, okay. Let me, okay, hang on. I put up gallery view so I could actually look at people when I'm talking to them. Let me take away gallery view. And let's go all the way back. Oh, there's the formula I want. Here, this formula. Okay, so here's the one-dimensional case, unoriented. V is a vector space of dimension bigger than 1. B is a non-degenerate bilinear form.
So remind me, this is the 1D TQFT?
This is the one-dimensional case, one-dimensional unoriented. So the data of the theory is a bilinear form in a vector space. Here, the dimension can be bigger than 1. Okay, so this is the gravity amplitudes on the exponentiated vector V. V is in the vector space V. Well, look, there's a global symmetry. If I rotate V by something in the automorphism group of the bilinear form, I get the same amplitude. To me, that's a symmetry. That's a continuous group of automorphisms of the quantum gravity amplitudes.
But do you think this is special to one dimension?
Definitely not. Definitely not. Let's oh, that is a shame. On my slides. Well, okay, the slide will suffice. It won't make the point as quite as clearly as I'd like, but I think I could get it across here. So here's the vacuum to vacuum amplitude. And so we have, look at the blue, the exponential blue, sum over the universes of lambda x. Now, supposing I have, supposing I have n universes, n components of the universe where the string coupling is the same in each connected component.
So like a ZN gauge theory in 1 + 1.
No, well, no, I'm just saying, let's take a Frobenius algebra. Okay, let me put it differently. Here's your general semisimple Frobenius algebra.
Yes.
So it's determined by this data theta sub x for the various idempotents. What if we have theta x's are the same?
Yes.
For different x's. Then there's a symmetric group that acts on the Frobenius algebra.
Yeah, I was saying that the ZN gauge theory is one such example in 1 + 1D, the BF theory.
Okay.
Yeah, but anyways, I understand your point.
Sorry. I see. Okay, good. So then I have that symmetric group symmetry, and that'll act as a symmetry of the amplitudes.
Right. You say the way. Well.
And so I don't have the formulas to flash up here for the case of dimension C bigger than 1, but they're in our paper and they're manifestly symmetric.
And the way that the symmetry acts is by exchanging.
Well, if I apply the symmetry, if I have some ingoing vector,
yes.
I have some ingoing set of circles. Okay, let's say this. I have some ingoing set of circles.
Yes.
And I choose a vector from each of these space.
Right.
And I apply the symmetric group action.
Yes.
Okay, then I'm going to get the same amplitude.
Yeah.
Same outgoing vector.
But does this symmetry lead to any selection rule on the amplitude? Usually the way the selection rules arise from a global symmetry is that I first act the symmetry on one state or one operator, and then I move it around to act on the other state. But here, since the interior region is being sung over, I don't know how to move that symmetry action from one state to the others.
Is there also a topological operator associated with this symmetry?
Yes.
I don't know. I'd have to think more about that.
Okay. All right. Thank you. Yeah, it's very interesting.
Thank you.
Shuhang, actually, I had a follow-up question on that discussion. Aren't there global symmetries just on the worldsheet theory? Like, if you take a 2D, the worldsheet theory as to quantum gravity, there's no problems with having global symmetry, right?
But here, the topology, the Bordism is being sung over, and that makes it confusing to think about the global symmetry of the seed TQFT.
But don't you do the same thing in worldsheet string theory? You also sum over worldsheets, and that's like summing over the Bordisms, right?
But then the original global symmetry of the worldsheet conformal field theory do not become the global symmetry of the string theory.
That's right.
I see.
Actually, earlier asked, is there a topological operator associated with the global symmetry? What the Greg was saying, is the answer positive or negative? Actually, I didn't get the answer.
The answer on my end is I don't know.
Does Shuhan know?
Well, if we're fixed seed TQFT, then the global symmetry can be implemented by a topological line. But here,
where does that line sit with respect to? I mean, what are the I guess the question is, what are the possible topologies of that line? If we're summing overall,
right. Yeah.
Right?
I was saying that before we sum over the Bordism, just for fixed seed TQFT on a fixed Riemann surface, then yes, the global symmetry is implemented by a topological line. I thought that was what Juben was asking. And then I guess it's more subtle when we sum over Bordism.
Yeah.
But before we sum over the Bordism, then yes, there is a topological line.
Sure. I mean, that's what you've been working on.
That's right. Yeah, but I that's how I interpreted Juben's question.
Okay.
Any more questions or comments from the audience?
By the way, so from the abstract TQFT point of view, you've already included everything, right? You included Z of S1 and Z of point. So where would the interfaces enter from that set? Right.
Well, I guess I would want to, I mean, I haven't really thought that much about it. Shuhang has. I would want to take two Frobenius algebras.
Right.
Right. and somehow have an interface between them. And
So the point is that it necessarily involves like thinking about multiple TQFTs at once.
Yeah, exactly. I mean, but maybe they just, come together into one bigger TQFT. I don't know.
I can say something about this. So this has been done somewhat by Gardner and Megas, where you fix some part of the bulk data rather than summing over all bulk data. So you take an interface in the bulk, fix it, and then sum over all topologies that respect that fixed bulk data. And you have two TQFTs on two sides of that interface. So you don't sum over all bulks in that case.
Okay, I should go back and look at that part of their paper again.
Okay. So in any case, I should thank Greg again. Thank you.
Well, thank you for the invitation to speak. Thanks for coming to the talk and staying to the end.
Thank you.
Thank you. Bye for now.
Righto.